And so the last thing that we may want to do is talk about this notion of how common is the transitivity that you observe in this particular network. So we have observed a number, right? So the global transitivity of Desert High School network was 0.26. But the common question, or I think the most natural question was, well, is that too low or is that too high? How does that compare to what happens overall, right? So for that purpose, there are different ways of analyzing that. And to do that, I'll show you one method. It requires a bit of computer power, so it depends on how large your network is and to make this calculation. And it requires StatNet. So we are going to load StatNet package. And if you haven't installed it, you'll have to install packages prior. And we're going to detach iGraph package because the two packages don't really, sometimes they're in conflict with one another, so it's better to detach one if you attach another. And we're going to run what's called this SUG test function. What that does is it looks at the at how frequent a certain feature that you're interested in occurs in a random network, and how does that compare to the network that you have. So in other ways, it a little bit helps you answer that question. How does the transitivity, or how is some other feature of my network, how does it compare to what would happen at random? And it generates the random network based on the feature that you specify. So to do that, I'm going to run an example to show you. And then I'll explain the output as to how this takes place. So we have just run a function, this g.test, over Desert High network. Please note that I didn't specify I in the beginning because I'm using the StatNet object that we had at the very beginning. Remember, we transformed Desert High network into an iGraph network. So because we're using StatNet again, I'm using that previous object. And so the results of these tests have been written into an object called CUG test trans, because we're looking at transitivity and we're comparing this network's, the Desert High network's transitivity to a distribution of random networks that have the same number of diodes as the network we're modeling. So we're randomly generating networks of the same type, and the type here is specified based on diodes. So let's look at the output of the test and plot it. And what we see is that this is the distribution here in the plot. So what that is these are the the observed transitivity of the network. So our transitivity is 0.23, and that is much higher. It's over here in comparison to the average transitivity within a distribution of networks that have been randomly generated using the same number of diodes as in our observed network. So we definitely can see that this transitivity is beyond what we would expect. For those who want to read more about this test, you can run this command. It gives you a bit of explanation, and I sort of put some explanation in here so you can read more. Just a different example, so just let's look, instead of looking at transitivity, you can use other metrics to compare. So for instance, density. Is the density of the Desert High School network any different if we randomly generate a distribution of networks of the same size, so the same number of nodes and edges. So we run this test, and we'll look at its results, and we see that the observed value is that, and if we plot the results, we can see that our density is a lot lower, which again, very low than that would observe at random. And again, low density means that the edges do not appear at random, and that there are some social processes that may explain those edges. So normally that would be a rationale, right? So this is clearly a human network, right? A network of social relationships. It's friendships, high school friendships. So we see that its transitivity, or the amount of closure within that network, that was the previous test, is a lot higher that would be observed at random, and that the density of the network is a lot lower that would be observed at random. And that is basically what you would expect actually in a human network. So you can also look at the centralization and run this command here, and so we see that the centralization of this network, so the network is less centralized than the average, but that really is kind of difficult to draw any conclusions from at this point. So I'm going to stop this tutorial at this point. The tutorial further continues to talk about cliques and communities. You are more than welcome to try it out and read about the different community detection algorithms and understand how you can plot them and see the differences between them. But that is not required for you for any assignment in the course. And this is just something for those who are curious and really want to run community detection in R. You can look at it. It's fairly straightforward, and I try to include a couple of different examples with explanations from the draft book on using R. So there is also a modularity detection algorithm in Gephi. So there is one way of community detection that's embedded within Gephi that you can use. But here you also don't really have to run those things, but you can just read the explanations and understand, get this sort of intuitive notion of what community detection represents. And for those particularly curious, I'll just say that the main thing that you may want to remember is that in computer science, or sort of when we talk about network analysis, community, in a sense of metrics and algorithms of community detections, does not actually imply a community in a social science sense of things. So it doesn't mean that you have people whose relationships are based on trust and who have some sort of underlying affection to one another, commitment or responsibility. It's just different computational ways of partitioning the network. So it's looking at how the network is structured and whether there are some subgraphs or some parts of the network that can be distinct, that are distinct based on the structure. And so to partition the network in these different parts, you can use different rules. So you may be looking at whether some edges lie between communities, so that would be one example, or you can be looking sort of at the similar positions of the nodes, and that would define that they are in the same community. So if you're interested in learning a little bit more about that community detection and looking closer at cliques and communities, just run through the script slides and lines of codes, and that should give you some insight.